Hello, and welcome to the Health Index app. This application allows you to compute the health index of your nanopore traces. This application is compatible with three file types, namely the ABF files from the Clampex software, ABF files from the Eager Pro, and the DAC binary files that are generated using LabVIEW. Information about these files can be found in the Compatible File Types document included with the Health Index application. The status button indicates whether the program is busy or not. Yellow means busy, green means available. After selecting the correct file type using the File Type drop-down menu, click the Select and Load File button and then click on the file that you wish to analyze. If the incorrect file type is chosen, an error will be yielded. The file name will be displayed in File field. Once you select and load the file, you will see trace attributes getting updated. For example, the sampling rate, input current unit, trace length, start time, and end time. It is also recommended to verify that the correct input current units are picked up by the application. The unit can be selected to be picked up from the header, estimated based on the current, or entered manually. Start time and end time correspond to the time window within which you wish to compute the health index. Under File Attributes, you can see the file information corresponding to the chosen file. If a binary file from a LabVIEW origin is chosen, the program expects to have a text file accompanied by this binary file. Information about these files can be found in the Compatible File Types document included with the Health Index application. The controls within the file attributes include precision, bytes per reading, data scaling factor, signal channel, header offset, data channels, endianness, and instrument string. More information about the instrument string can be found in the Compatible File Types document. The signal channel is important for multi-channel files. By default, we expect the current to be in channel number 1. If this is not the case, this should be updated. The No DDC stands for No Data Type Conversion. If you change any of the file attributes, please click the Update FATA button to update your selections. Now let's navigate to the Calibration tab. Selecting the Use External Calibration Values radio button enables the table below. The standard deviation range determines the span of each calibration feature. The span is defined as mean plus or minus threshold times standard deviation, where threshold is equal to the standard deviation range field value. It is only active when the table is inactive. There are 6 features in the table: root mean square of the current, mean of the current, slope of the current, skewness, 1/f noise coefficient, and line noise. More information can be found the SI of the paper titled Gateway to Data Visualization and Analysis in Solid-State Nanopores. Please note that we are viewing default startup values of the table. These will get update when the health index is computed, while Use External Calibration Values option is deselected. In the table, the upper and lower threshold of each calibration feature is defined using the max and min columns. If any feature of the column is changed, please press Validate button to update and validate the entries. This is especially important if the weights are changed, since the sum of the weights should be equal to 100. The table can be saved using the Save Table button. An external table can be recalled using the Load Calibration button. When the Use External Calibration Values radio button is selected, window size, calibration windows, PSD type, line frequency min, and line frequency max options gets disabled. This is because these features are no longer needed to establish the calibration baseline of the health index and are defined using the values in the table in the Calibration tab. After selecting the span of the trace within which the health index should be computed, navigate to Step 2 panel. If there are events in the trace and you want to remove them to isolate the baseline, select the Remove Events option. It enables the baseline tracking and event removing options. We will be using the Remove Events option for the trace file we are going to use. The operations of the baseline tracking and event removing options are identical to the options present in the HyperExtract software. We would refer interested readers to the HyperExtract Tutorial 1 for more information. Afterwards, click the Test Baseline Isolation Method button to see if the program is correctly picking up the baseline points of the trace. The isolated baseline points are highlighted in red. We can see the trace we have loaded contains plenty of events, and the application successfully isolates the baseline from the events. Note that this plot is limited to 10 million data points. If the trace length is longer than this, the end time will be changed to match the data cap. Please make sure to check the end time field. Ensure that it has not changed after clicking the Test Baseline Isolation Method button. Afterwards, navigate to Step 3 panel. Window size defines the calibration step size. The trace during the calibration phase is evaluated in segments whose size if defined by the window size field. Total windows are the total number windows of the trace used for poor health index computation. We will call this trace length as the active trace. If start time or end time is changed, the total windows change accordingly. Total windows is defined as window size times the active trace length. Calibration windows defines the total windows or segments used to establish the values of the calibration features from which the poor health will be computed for the rest of the active trace. Calibration length cannot exceed 80% of the active trace length. If this condition is violated, the application will warn the user during the health computation. Calibration length is updated based on window size and calibration windows inputs. The health window size defines the window segment size used for poor health index computations. That is, the health index features are calculated along the post-calibration active trace in segment sizes, defined by the health window size. The health segment length is the health window size in seconds. Choose the PSD type from the PSD type drop-down menu to compute 1/f noise coefficient and line noise. Line frequency min and line frequency max are used for the calculation of line noise. The program looks for the highest noise component within the range defined by these two fields and assigns it to as the line noise. Now let's navigate to the Step 4 panel. It contains options to low-pass filter the trace. To enable low-pass filtering, click the Low-Pass Filter Trace radio button and a host of options will become available. LPF stands for Low-Pass Filter. You can set the LPF in kilohertz. For the LPF type, there are several options available. Depending on the type you have chosen, the ripple lengths and stop bands will become enabled. For the LPF method, there are two methods, the fast method and the better method. We recommend the better method. The order of the filter is defined by the filter order field. Before moving to the Step 5 panel, let's compute the health index. To do this, click Compute Health Index button. You can track the progress under Progress Percentage field. As seen, three figures appear. Figure 2 and 3 are the health propagation figures with weighted and absolute values. In the case of weighted values, the weights in the table under the Calibration tab are taken into account, while in the case of absolute evaluation, those values are disregarded and all features are weighted equally. If we now navigate to the Calibration tab, we can see that the table has got updated. Figure 1 is called the Feature Analysis Dashboard, which showcase how each feature behave in the post-calibration active trace length. Now let's navigate to the Step 5 panel. This is used to change the aesthetics of the plots. Show individual plots. If selected, the 6 figures in the Feature Analysis Dashboard figure are plot as individual figures. Subplot type sets the figure's arrangement for the Feature Analysis Dashboard figure. Spacing sets the spacing of figures in the Feature Analysis Dashboard figure. Font size and label size changes the font and label sizes of plots. Widths of lines for plots and thresholds and their color options are provided here. Grids of plots can be controlled by the Grid drop-down menu. Under the Reporting tab, you will see a field that reports total violations. This corresponds to instances where features cross the threshold limits defined in the table under the Calibration tab. Total violations are expressed as a percentage in violations percentage field. Evaluation time in seconds and the real-time progress percentage options are also available. Now let's navigate to the Health Plot Limits tab. Deselect Auto Limits radio button to enable X and Y limits and tick options for Figure 2 and Figure 3 pop-up plots. Click Replot to apply any of the Step 5 and plot limits to the figures. Now let's navigate to the Custom Plot Styling tab. In here, you can write a custom script to change the styling of Figure 2 and Figure 3 pop-up plots. These scripts can be saved and recalled using the Save and Load buttons. By default, while we have provided an example code, they are commented out to be inactive. The Replot and Compute Health Index buttons are linked to the Replot and Compute Health Index buttons in the Health Index tab. This brings the tutorial to an end. Thanks for watching.